So in this session on signals and systems, we are going to study how to write a program for calculation of discrete time Fourier series. Okay, but before we get into the program, let us revise our basics of discrete time Fourier series, also define discrete Fourier transform and study the relationship between the two. So discrete time Fourier series, as we studied last time, xn is a periodic signal whose period is n, that is, it repeats after capital N number of samples. Xk is the Fourier series coefficient that you calculate, and as we noted last time, one major difference between continuous time Fourier transform, continuous time Fourier series and discrete time Fourier series, that the frequency spectrum also is periodic and its period is also equal to n. So note that in this case k represents the frequency index and n represents the time index. So this equation is useful for calculating the Fourier series coefficients, and if the Fourier series coefficients are known, then you can calculate xn by using this equation. Now there is a transform called as discrete Fourier transform, which is related to discrete time Fourier series. So let us see the definition for this. Discrete Fourier transform is defined like this. Now if you compare this equation with that of discrete time Fourier series, you can see that the only difference is that in discrete time Fourier series you got division by n, which is absent in this case. The sum term is the same. Now the reason for studying discrete Fourier transform is that in MATLAB the function that is available for calculation is basically for discrete Fourier transform, but there is no problem in that because you calculate discrete Fourier transform and divide it by n in order to get discrete time Fourier series. So that is one reason for studying discrete Fourier transform. There is another reason which we will study later on, that it will be useful for calculation of discrete time Fourier transform, which we have not studied so far, but it will be useful for that also. So obviously its inverse Fourier transform will be given by this equation. So in this case you got n in the denominator here, and for the corresponding discrete time Fourier series you do not have that. Alright. So what we are going to do is to study how to write the program for calculating the amplitude spectrum and the phase spectrum of a given signal by using discrete Fourier transform. Now this discrete Fourier transform is called as a fast Fourier transform in MATLAB, and basically fast Fourier transform is the technique for calculating DFT. So it's basically DFT itself, but the manner in which it is calculated leads to high speed calculation. That is why it is called as a fast Fourier transform. Okay, so how do we use this function? So XDF is some variable in which the fast Fourier transform of x is returned. So x is some function of n, and by using FFT you can get XDF. But as we have seen, the discrete Fourier transform, using this, if you want to obtain the Fourier series, you have to divide this by n. So to find the Fourier series coefficient, you calculate XFS. So this is discrete Fourier transform DF. This is XFS, the coefficients for the Fourier series. So you divide XDF divided by n. Then XFS is a complex quantity. So you calculate its magnitude by using the absolute function, absolute of XFS. So it will give you the magnitudes, and you calculate the phase by using the angle function. So XA stores the phase of the XFS. So using X and XA, then you can plot the amplitude spectrum and the phase spectrum. Alright, the question is, how do you choose n? The answer is, ideally it should equal the period of xn, that is equal to capital N. If that is the period of xn, in your FFT calculation also you choose n to be same. It's not absolutely essential, and we'll see what to do when n is different than the period of xn itself. Okay. So as we said, you calculate the amplitude spectrum by obtaining x and then plot it as a function of k, which is the frequency index, or k by n, which is the digital frequency itself. Okay. Then you can plot phase spectrum. So plot xa as a function of k or k by n, which is again a digital frequency. Now, one important thing to note is that whenever you do computation through any program, you will not get absolutely perfect values. Errors will be small, nevertheless, there will be some errors. Now, the inaccuracies in calculation can give errors in amplitude and phase spectrum. This is called as spectrum leakage. That means you may see components in the frequency spectrum calculated at frequencies which are not even present in the original signal. So that is called as a spectrum leakage. However, these inaccuracies usually do not cause much problem in the amplitude spectrum. But the phase spectrum is rather sensitive, and you will find you will get lot of leakage in the phase spectrum because of the inaccuracies in calculation. So as we said, phase spectrum is more sensitive to inaccuracies in calculation. So you will see phase even at absent frequencies, even those frequencies which are not present in the signal, even at those frequencies you will get some phase angle. So to avoid this phase leakage, what you do is you make phase 0 whenever amplitude is smaller than, let's say, 1% of maximum amplitude. 1% is a ballpark figure. So what you do, you make xa, which is the angle or the phase of the spectrum, equal to 0 whenever the magnitude of x is less than 1% of maximum value of the x. In that case, you will make the phase leakage disappear. Okay. Let's now write a program which will calculate the frequency spectrum of this particular signal. So xn, as you can see, it has got two sine waves, and the digital frequency of the first one is 1 by 5, that is 0.2, and for the second one it is 2 by 5, that is 0.4. So when you calculate its frequency spectrum and plot it, you expect to see two lines, one at 0.2 digital frequency and one at 0.4 digital frequency. So as I said, this is repeated here, two digital frequency components, one at 0.2 and the other at 0.4. And since this is a double-sided spectrum, you will also get these components at minus 0.2 and minus 0.4. Remember, amplitude spectrum will be an even function of frequency and phase spectrum will be an odd function of frequency. But FFT function calculates only the positive side of the spectrum, and later on we'll see how to take care of it. But right now understand that when you plot FFT, you will see only the positive side of the spectrum. And also, since the spectrum repeats around 1, remember, it repeats around 1, which is the digital frequency. So you will also get components at 1 minus 0.2, which is 0.8, and also at 1 minus 0.4, which is equal to 0.6. So we are going to verify this. Okay. And since these are sine functions, and basically Fourier series is calculated considering the cosine of the reference, you will get minus pi by 2 for this as well as minus pi by 2 for the phase in this case. So we are going to verify this through the program. So let's look at the program now. So clear CLF, CLC as usual. Then n equal to 5. We choose n equal to 5. Later on we'll see if you choose n equal to something else, what will happen. Then you define your time index n equal to 0 to n minus 1, and also frequency index. Remember, for discrete time Fourier series, the frequency index numerically is same as the time index itself. So that is 0 to n minus 1. Then you define the digital frequencies in the signal that you are going to generate. So let's say k1 equal to 1 and n1 equal to 5. So we have chosen this n equal to n1 itself in this particular case. And then you define your signal. So that is sine of 2 pi n k1 by n1. So there's 1 by 5, digital frequency 0.2 as we said. And then the second harmonic is 2 times this, so that will be at 0.4. But we are choosing its amplitude, which is half the amplitude of the fundamental. It's not necessary, but for illustrating, we are choosing the different amplitudes. Okay. Then you calculate the discrete Fourier transform by using the FFT function. Then you divide this by n in order to get the Fourier series coefficients. Then you get the magnitude spectrum by calculating the absolute value of XFS. And then you calculate the phase by using the angle function. So XA equal to angle of XFS. So it's now a question of plotting X as a function of K by N as a function of digital frequency. That will give you magnitude spectrum. And then plotting XA as a function of K by N again, that will give you phase spectrum. So that is straightforward. So subplot 211 stem K by N. Mind you, on the x-axis we are plotting digital frequency. So it's K by N, X is the amplitude. This line width, etc. X label, Y label and so on. So we know how to use these statements. So this will plot the amplitude spectrum. Then you plot the phase spectrum. So again K by N, the x-axis is same. But on the y-axis now you plot the angle, so that is XA. And the rest of the statements you already know how to use them. So when you execute this program, the amplitude spectrum you will get like this. So you have plotted digital frequency on the x-axis, so it goes from 0 to 0.8 and you get one component at 0.2 whose amplitude is 0.5. Remember, this is a double-sided spectrum. So for each side, it is half the amplitude. So fundamental had amplitude of 1, but double-sided spectrum, it will become 0.5 for the positive frequency and also 0.5 for the negative frequency, which is of course not plotted here. Then the second harmonic you get at 0.4 and its amplitude is half, so it becomes 0.25. And as we said, since this is repetitive, you also get amplitude at 0.6 and also the amplitude at digital frequency equal to 0.8. And as we saw for both, since both these are sine waves and cosine is the reference, so we get minus pi by 2 as the angle for both these frequencies. And of course, since the phase spectrum is an odd function of frequency, here you get positive values. So as we said, these plots show only positive frequency spectrum. But understanding that amplitude spectrum is always an even function of frequency, you can manually always extend this to negative frequencies also. In our next session, we will also see how to take care of this, how to modify the program so you can plot both sides of the spectrum. But right now, we are plotting only positive side of the spectrum. Okay. So this was plotted for n equal to 5. Now, if you plot this for n equal to 50, when n is so large, you will find lot of leakage in the phase spectrum. This is because we have not set the phase angle to 0 using that particular condition, which we have explained before. So if you use that condition now and again choose n equal to 50, so what you have to do, as we said, XA is the angle of XFS and you make XA equal to 0 whenever the amplitude of X, which we had called as X, is 1% of the maximum value of the X. Okay. So now when you utilize, so this is an additional statement that you have to insert in the program. So I'm not showing the entire program again, but you can show that now the leakage in the phase spectrum is removed. So in this particular session, we have defined Fourier, discrete Fourier transform. We have seen how to use it in order to get the discrete time Fourier series. And we have also studied how to choose n. We have talked about the spectrum leakage and how to avoid this leakage. And that's all in this particular session.